So welcome everybody tonight for this webinar. I'm just introducing SCAR. A few words for those who don't know what SCAR is. SCAR is international thematic organization of the International Science Council, and is in charge with initiating, developing, and coordinating high-quality international scientific research in the Antarctic region and in the Southern Ocean, and has also a very important role in advising, consulting for the Antarctic Treaty meeting for the conservation and protection of the Antarctic environment. Since its first meeting in 1958, SCAR has been supporting international science with many events, and also support senior scientists and junior scientists with fellowships and awards. Is curating the management of library and data, and has a very important produced a very important outcomes from also for policy advice. This SCAR is managed by by the executive committee, which is composed by the Professor Gary Wilson from New Zealand, is the president, who is elected by the SCAR delegates from all nations, who runs Antarctic programs, and 4 vice presidents from the one now in charge at the moment. They are Carlota Escuzia from Spain, and then Marcelo Elepe from Chile, Takuji Nakamura from Japan, Burksu Ozgoy from Turkey, and they're also supported by the Secretariat and by the Executive Director Chandrika Nath. The executive committee is elected by the SCAR delegates, and it works for 4 years, and then they are renewed. In particular, the Geoscience group is led by Jesus Galindo from Spain, the one to the right in the picture, from Naresh Pant from India. Actually, I can use the pointer. Okay. That's Jesus, who is also participating tonight, the webinar. Naresh Pant from India, he couldn't attend tonight. Myself as a secretariat from Italy, and Matilde Ferrante from Italy. She's got a fellowship to support the three of us with a mandate of 2 years. So for those who hasn't subscribed the Geoscience mailing list yet, so please use the code or write to the mailing list later, because we spread our news and information via our mailing list. And how the SCAR is organized in thematic groups, scientific groups, which are the geoscience, the life science, and physical science groups. And there are also standing committee for the data management, the geographic nomination, the Antarctic Treaty, the relationship with the Antarctic Treaty, the finance, of course, and the human and social sciences. And then there are research programs. There are different disciplines in space, in climate and future prediction, on Antarctic ecological conservation, ice sheet instability, and there are also cross-disciplinary action and expert groups. The geoscience in particular deals with the specific aspect of concerning the geoscience, of course, and they are, for example, the ADMAP, the Antarctic Digital Magnetic Anomaly. They are in charge of collecting all the data and compiling Antarctic maps, international bathymetric chart of Southern Ocean. For example, they are collecting also bathymetric data from different countries and make a compilation of the Southern Ocean. Or the volcanic, the Antvolk, which is also mapping different volcanic bodies around the Antarctica. But then there are also cross-disciplinary groups like RINGS, which is focusing on the grounding zone data collected along the Antarctic perimeter. Tonight we will know about GIANT, the geodetic infrastructure of Antarctica, from Mirko and Domitilla, and later we will have a few more webinars starting from October 21. The next one will be the groundwater from Roger and Gilles. And then the Antarctic Seismic Data Library on October 28th, and then AntPass, the Antarctic Permafrost. And we will close our series with the GeoCon, the Geological Heritage and Conservation. So if you haven't done it yet, have a look to the schedule and put them in the agenda for the next webinar. So I'll now leave the floor to Mirko for the GIANT webinar.
Yeah, thank you, Laura. My name is Mirko Scheinert. I'm affiliated with the Dresden University of Technology in Germany, and together with Alessandro Capra from Italy are chairing the Geodetic Infrastructure in Antarctica expert group. And first of all, I would like to acknowledge the entire group. So, because during the years it was a nice cooperation, of course, and I think I will also present it today. A lot of results could be produced. So let me start with the overview about on the program objectives very shortly. So of course we would like to support and encourage the development and maintenance of geodetic infrastructure in Antarctica. I will come in a moment to that because to give a critical view on this point. Closely linked to that is the maintenance of the reference frame, not only in the regional reference frame, but also using the geodetic observation in Antarctica for the realization of the global reference frame. And then, of course, we have a lot of data and solutions and products which support the investigation of geodynamics. Here I have to mention especially glacial isostatic adjustment. We also try to maintain a close multidisciplinary cooperation, especially with the SCAR scientific program Instant and further entities. And one important point, I think this is true for entire SCAR, is to provide information both on technology and on data, and also to give or to enable free data access, open data access according to the FAIR principles. This is an important point, I think. We also try to support scientists of neighboring disciplines to apply geodetic techniques, for instance, GNSS. And last but not least, communication and outreach, and of course, the support of the mobility and education of early career scientists. I mean, this is one point being at the university where we are working on in getting projects and raising funding in order to have PhD projects and to teach our early career scientists, yes. Yeah, so this is like a kind of outline because in GIANT we have having working groups or topics, mainly these four, with permanent geodetic observatories, with tide gauges, with the gravity field, and then with GNSS observations. And I will go briefly through these different topics. Of course, I cannot be complete, or it will not be complete. And for that, I also would like to refer to the literature, to the papers, to the wealth of information, which is, of course, available. And of course, people who are interested, scientists or the public, can contact us. Okay, so let me start with a view on geodesy and the connection to critical infrastructure, because this is an issue which has been brought up for some years now. We speak about so-called essential geodetic products, which means that we especially serve the global community to provide consistent reference frame solutions. That means we speak about the terrestrial reference frame, but also the connection to the celestial reference frame, which is an inertial reference frame, and also the positioning of satellites. And this does not only hold true for GNSS, or the Global Navigation Satellite System, but also for a lot of other satellites like imagery, altimetry, gravimetry, and so on. This has been brought about also in the United Nations. So several years ago, there was like a resolution on that. And I think 2-3 years ago, the so-called United Nations Global Geodetic Center of Excellence was founded and is now, or the home is given in Bonn in Germany. And there is a small group working on that, and they defined the so-called global geodesy supply chain. You will see it here in this simple graph, where you have a number or a lot of observatories. You produce data, you have to analyze it. So for that, you have to have analysis centers in order to come up with geodetic products, which aid a huge number of further applications, which really influence our daily life. And this is something because all these observatories, these data centers and analysis centers and so on have to be maintained and have to be paid somehow, right? So it's done by, let's say, state authorities, local authorities, institutions. There is a lot of compulsory work so that this can be maintained. And this is a real problem if we, let's say, cut out pieces of this global geodesy supply chain. And you will also see, of course, that geodesy provides products which are critical to essential areas of climate science in a broader sense. I have given here some of the points. So for sea level, for vertical land motion, for the monitoring of ice sheets and glaciers, but also for atmospheric sciences and oceanic circulation. Yeah, so to give you some background for that, I start with the permanent geodetic observatories. Here, first of all, I like to mention the 2 stations, the only 2 stations in Antarctica, which host the so-called VLBI, Very Long Baseline Interferometry. This is a technique where we can link the celestial reference frame and the terrestrial reference frame. So the one is situated in Chiova in the Atlantic sector of Antarctica. You see it here on this small map. And the other one is at O'Higgins, where at the Chilean base, O'Higgins, the so-called German Antarctic receiving station, is situated. You see here the VLBI antenna. And with these antennas, with this technique, we can span the baselines over the continents. So you see it here from Australia, for instance, to Chiova in Antarctica, and then further to South Africa. And this technique is essential to get, as said, the linkage between the terrestrial reference frame and the celestial reference frame. This is a global map, so don't be spoiled with that. What I would like to show here that especially for the technique of VLBI in Antarctica, we have these only 2 stations, so as said, in Huygens and in Jehovah. And this is really critical. If it would not be possible anymore to run these observatories, we would have really problems. I can, let us say in this way. So the reference frame we are working with is called the International Terrestrial Reference Frame. The latest realization is the ITF 2020. You can have a look here at the website and so on. There are regular updates on that. And besides VLBI, which is an important technique, of course, other techniques are also contributing. So the French DORIS, the GNSS, and SLR is satellite laser ranging. Especially SLR is the only technique which can directly access the geocenter due to the satellite orbits. Yeah. Second point, I would like to give some information about tide gauges. This is, in my view, a complicated issue because it's really hard and difficult to run tide gauges in Antarctica due to ice coverage and the change of the season. So let's say with open waters and sea ice in the vicinity of the stations. But it's very important to have these instruments because we are able to monitor relative sea level and change of relative sea level, and of course also to interlink the regional and global mean sea level with the ice mass balance and the vertical land motion. I just give here some examples here in the bottom in these graphs. You see a number at least of these tide gauge data or tide gauge stations where data was available. The problem is that only a few of these stations really continue to record data. And on the right-hand side, there's another application where we can use the tide gauge, the local tide gauge time series to validate ocean tide models, which is important not only for Antarctica, but also for the global ocean. And we see a lot of applications, of course, not only in oceanography, but also, for instance, for the reduction of satellite altimetry and so on. An important issue is here that we aim to co-locate the tide gauges with GNSS because by the co-location with GNSS, we get automatically a reference to the terrestrial reference frame, which I showed before. And also this point here, the third point, we can do the interlinkage between the regional and the global mean sea level change and to combine it with the mass balance and vertical land motion. And a nice example is here given recently by this publication of Reswani et al., where they used tide gauge data and in combination with satellite altimetry at the western coast or part of the Antarctic Peninsula. You see it here. And they were able to combine it with the time series with GNSS time series to illustrate the vertical land motion. And what we can see here, there is a distinct, change of the rate of uplift after the Larsen B ice shelf breakup in 2002. And this can also be observed by the tide gauges here. Yeah, this third point refers to gravity field. Here we use a multitude of different techniques to realize gravity measurements. I just listed them here just for a brief overview. First of all, we have absolute gravimetry, which provides a reference for relative gravimetry, but also for geodynamic applications if we combine gravity change and height change. Honestly, this is also very difficult because all the masses or the mass changes which occur around a certain site have to be observed and have to be taken into account. Then we have terrestrial relative gravimetry. I made a distinction here because here in this kind of gravimetry, we use spring-type gravimeters like Lacoste-Romberg or Syntrex in order to carry out gravimetric surveys. Or in a stationary way, we can do tidal gravimetry, which then can also be used to infer ocean tidal loading and also to validate or to test ocean tide models. Another type of gravimeters, which is an example, is shown here also from Kiowa station, is the so-called superconducting gravimeter, which is able to measure within precision 1 order of magnitude better than the usual spring-type gravimeters. With that, it's more like laboratory instruments, but we can infer very precise time series in order to investigate Earth tides, ocean tidal loading, but also further geodynamic applications. And normally these time series observations are then also combined from time to time with absolute gravimetry to check the time series and also the drift of this time series. And when we speak about gravimetric surveys and you think about Antarctica, then of course we have to have airborne methods because this is the only way to get close surface measurements of the gravity field over large areas, right? So because otherwise it would not be possible. And this so-called airborne gravimetry, and I also added UAV-borne gravimetry, made a big development, a huge development in recent years. In my view, we saw already the transition from the traditional spring-type gravimeters to so-called strap-down gravimetry using inertial navigation systems. And of course, the gravimetric surveys are not only used for geodesy, but also for geophysical applications. Yeah, you see it here, just for example, some of the pictures. Here is one of the INS, which have to be thermally controlled, and you also have to calibrate them. But in recent years, very good experience has been made with that. And of course, a number of different aircraft are used not only in recent years, or in the past, but also in recent years, for instance, in the RINGS project. Yeah, with these gravity measurements, we are able to infer a regional gravity solution for Antarctica. We sometimes also call it regional gravity field improvement. And this is one of the proper geodetic tasks because geodesy cares for the shape of the Earth, but also for the exterior gravity field of the Earth. And here we see a close linkage to the International Association of Geodesy, where we have a similar group, I would say, which is called Gravity and Geode in Antarctica. And recently we had an update for this regional gravity field solution. So the first solution was published in 2016, and until the pre-COVID time, so to say, it was possible to include a lot of new measurements. I mean, now we have even more new measurements, so it's still needed to update this solution. We have now a resolution of 5 kilometers, also in improved processing. And all the data are published at Pangea, so are available to the public, to the scientific public. And these products include gravity anomalies, gravity disturbances at different heights, the height anomaly, which is close to the geoid, but also the second radial derivative, which is the first derivative of the gravity anomaly, Bouguer anomaly, and also some accuracy measures. By the way, this was a project which was realized by my colleagues from Munich and myself with some funding from the German research foundation prior to the program Antarctic Research. And this is also one thing, maybe I can refer to that, where we educate the the early career scientists. So these are all projects where PhD students worked and then finally did their PhD. Yeah, so just to give you a glimpse of that, so this ANGG 2021, how it is called, gives you products in terms of the gravity anomaly, but also some accuracy measures here in terms of standard deviation. In this map, in the standard deviation map, you nicely see, of course, where the surveys are located. Yeah, because let's say all these airborne surveys, you have a higher accuracy or higher, accuracy or or lower standard deviation than in other areas. And of course, the gravity information here in this gravity anomaly map incorporates a lot of information which can then be used for further applications. So for instance, for inversion techniques in geophysics and so on. Just for completeness, we also inferred the height anomaly, which is an important reference surface. If we speak about the geoid, so the geoid is the equipotential surface of the gravity potential. So the quasi-geoid, which is shown here, is close to that. We can also provide the Bouguer anomaly, and this is the lower map here. On the right side is the second radial derivative. As said, we can use these products for further applications in geophysics and geodynamics, and especially to infer or to do different type of inversion. Here, a nice example is given, published just recently in order to infer the subglacial topography and the transition zone between the ocean and the continent. I just cut out here one of the pictures or graphs, and you see here, this is in the Atlantic sector, a number of ice shelves in this region of these ice shelves. The gravity anomaly data set was used in an inversion scheme to infer the bathymetry. And for all these ice shelves, I've given the names here. So for instance, for Borchgrevink here, we inferred more accurate bathymetry as given here, or for instance, in the Fimbul-Isen, you can see that we could infer much more frequency, so to say, in the subglacial topography. Of course, there is also a close cooperation with the action group RINGS, because whenever geophysical airborne measurements were done using an ensemble of different instrumentation, then whenever also strap-down gravimetry was flown, then we can use that also for our geodetic tasks. So that means we still have to update these products when new data sets will be incorporated. And this is relatively new. We also have a new initiative and applied for funding, so I hope that this will be coming. So in order to get a pilot study to see how new data can be combined into the existing compilation by some kind of open and automated processing. So I hope this will become, and I will be happy, or will be happy to report on that in the future. The fourth point deals with GNSS observations, where GNSS stands for Global Navigation Satellites, and we use this in a geodetic manner, where we are able to very precisely infer coordinates. So normally for the horizontal, we speak about 1 to 3 millimeters, and for the height, let's say for 4 to 5 millimeters precision for the coordinates. And this can be used, of course, in a number of applications. Again, this is closely linked to our neighboring or cooperating entity in the International Association of Geodesy. And when I look back into history, so to say, it was mainly episodic GNSS campaigns where we started from. Also to get an densification for the reference frame, but I have to say that more and more than permanent GNSS sites were installed and are still running. It is important to get the metadata information, and also to develop standards for the permanent as well as for episodic sites in order to approach the goal for a consistent processing. And then, of course, we aim to provide network solutions and share the data and provide products. So a major success, I would say, is the realization of the Giant Regain project, where the aim was to provide consistent coordinate time series, and this was done for the time frame from, you see it here, from January 1995 to December 2021. And I think this is a very nice example for the cooperation within SCAR, because due to the SCAR family, so to say, it was able to obtain all the data back to the mid-90s, which was more or less the beginning of GPS work in Antarctica. And within this project, we had 4 processing centers. So our university, or my university, then the group of Matt King in Hobart at the University of Tasmania, the group of Terry Wilson at Ohio State University, and the group of Peter Clark at Newcastle University in the United Kingdom. Also here, just a few words on that. We could use more than 280 sites, both continuous or permanent and episodic sites. And the average time base of the observational data was more than 10 years, which means this is the time frame from the first to the last observation in the time series. And which is very important is that many national programs contributed data, even if there is only 1 station, for instance, or 2 stations, which is very, very valuable, and I'm very grateful for that. You see the distribution of the sites, and we tried also here in the map to a little bit show the affiliation of all these different GPS stations. And what is also remarkable is that we could include sub-Antarctic islands, or like here the South Orkney Islands or South Georgia, which is located here. Yeah, you see here in the picture one of the typical examples of the setup of a permanent site. The products of Giant Regain were published, as said. So the publication, the paper itself, is found here at System Science Data, and the data is available at Pangea, and it includes the combined coordinate time series with, at last, then, or the last step, also the non-tidal atmospheric loading reduced. We also provide time series of tropospheric zenith path delay. These were not combined because these are individual solutions of the 4 processing centers. We provide the site information, which is important in order to reprocess the data, and also the list of events, because we have, in some cases, a lot of discontinuities of these time series. And you see some examples here. So for instance, here from the Antarctic Peninsula, so a typical discontinuity due to an earthquake, tectonic event, where you have a post-seismic relaxation. You can see it here in the north direction, in the north coordinate, with this sudden jump here, and then the relaxation after that. the right down, or here this lower graph gives more like a textbook example. So I mean, I would be happy to see all these time series like this, but this is only very rarely the case. More often we have to deal like with here in the West Antarctic side, Inman mountain here, that we have discontinuities also to different effects. Okay. Yeah, to give an outlook, this is just like a product, right? And I always say now the science can start. So we can use these coordinate time series now for further analysis and geodynamics, and especially the inference of displacement rates will be subject to subsequent investigation. And of course, people are starting with that, downloading the data and analyzing the time series. And we are already in the stage of planning follow-on of giant regain in order to include new stations, to extend the time base, of course, but also to fulfill or to do further improvements in our processing in order to increase the level of consistency. And you see here, again, the one backbone of this entire processing is the realization or linkage to the proper reference frame. Here on the right-hand side, just due to a preliminary analysis, you see the vertical displacement rates here color-coded, which still include both the elastic present-day effect, so to say, and the GIA part, maybe also other constituents to the location. And the arrows show the horizontal displacement rates, which includes still the plate motion due to the Antarctic plate. But of course, you already here, you can nicely see here the opening of the Bransfield Strait in the northern tip of the Antarctic Peninsula, between the peninsula and the South Shetland Islands. Yeah, this brings me already to my conclusions and outlook. I hope I could show that geodesy provides critical infrastructure for a number of essential core services. With that, we have essential tools for climate sciences and geosciences in Antarctica. I have given a number of examples. I don't have to repeat them here. I would like to mention here the problem which we are facing now, which is a real severe problem, and this is the decommissioning of a large number of GNSS sites, especially from the US PolNet ANet network and from the UK network. And this is one issue we are dealing with in the community to find ways how to deal with that and maybe to resume observations in the future. We also have a close link to SCAR Instant, especially to the subcommittee probing the solid Earth and its interaction. But also, as I've shown, to the International Association of Geodesy and to other SCAR groups like RINGS, but also to, for instance, to AGATA, the research program which deals with Antarctic geospace and atmosphere research. As I shown in the giant regain products, we also published the troposphere zenith path delay time series. And of course, we also deal or discuss the structure of each giant, or how to continue. So this means we will do an evaluation and revision of each giant. And I'm really looking forward to the next SCAR meeting in 2026, which will be a major milestone for the development of giant. Yeah, with that, I would like to stop. I also listed some selected references. This is, of course, also incomplete, but you can read it afterwards when the talk is published, and I leave it here with the conclusions. Thank you for your attention, and I will be happy to take questions.
Thank you, Mirko. Domitila, are you continuing to say a few words? Then we ask for question.
Yes. It's gonna be my pleasure. So I am going to share my screen. And now in theory, you should be able to see my slides, right?
Yes, we do. Yes.
Okay. So good evening, everyone. First of all, I would like to thank Professor Scheinert and Professor De Santis for the introduction. As I mentioned, my name is Domitila Forina, and I am a first-year PhD student from the Italian National PhD Program in Polar Sciences at Ca' Foscari University of Venice. I will give you just a quick overview of the geodetic infrastructure that is managed by the Italian Geodetic Observatory in Antarctica. And I will be focusing on GNSS stations, both permanent and episodic. Then I will give you just a quick list of some of the main results that can be obtained from the processing and analysis of a long time series of GNSS data. So first things first, the Italian Geodetic Observatory in Antarctica was established in 1998 within the framework of the SCAR expert group on geodetic infrastructure in Antarctica. IGOA was funded, as it still is actually, by the Italian National Research Program in Antarctica, also known as PNRA. The main goal of the observatory is not only to help and support the monumentation and management of geodetic infrastructures, but also probably mainly to collect and make the data available for processing in order to give us the possibility to deepen our knowledge on geodynamic and tectonic activities in the studied areas. The activity of IGOA is mainly conducted in northern Victoria Land, which is located in the East Antarctic Platon, and specifically in the area around Terranova Bay, where the Italian seasonal base, Mare Zucchelli Station, is located. Throughout its history, the observatory has managed and collected data from several different GNSS stations, one tide gauge, and several gravimetric measurements. But now I would like to focus our attention on the GNSS infrastructure that has been and still is managed by the Geodetic Observatory. As I already mentioned, the observatory was established in 1998, and in that same year, the first permanent GPS station was installed in Terranova Bay with the ITRF code TNB1. Simultaneously to the establishment of the observatory, though, the interest in investigating the peculiar geological and tectonic setting of northern Victoria Land increased. Indeed, as we can see from the image in the right-hand side, the northern Victoria Land is characterized by the presence of a known Cenozoic fault framework. So in order to collect evidence of the neotectonic activities present in the area, a network of nearly 30 GNSS stations was established, and it was called Victoria Land Network for Deformation Control, aka VLDEF. VLDEF was surveyed periodically throughout more than 15 years. The acquisition usually were based on sessions lasting 24 hours, but typically at least 72 hours. And it allowed us to collect a huge amount of data that helped us understanding better the nowadays activities occurring in the region. However, in 2017, the VNDF was dismissed, even though some of the stations actually are currently still working. Indeed, the nowadays GNSS infrastructure managed by the Italian Geodetic Observatory in Antarctica is composed by 3 different groups. The first group is composed of the 2 permanent GNSS stations that are located in Terranova Bay. These stations are TNB1 and TNB2, and they are installed approximately 600 meters from the Italian seasonal base Mario Zucchelli. TNB1 and TNB2 are able to acquire data continuously, 24 hours per day, 365 days per year, thanks to the fact that they are connected with a direct cable connection to the electrical power that is present in the base. Then through the collected data are automatically downloaded into a modem that is located within the base, and the data are retrieved during the opening season of Mario Zucchelli Station, which usually runs from late October to early February. Then the second group of permanent station was established in 2007 together with TNB2, I'm sorry. And these 2 stations, VL05 and VL18, are located in remote sites, respectively in Cape Phillips and in Nunatak. And they actually were originally 2 vertices of the aforementioned VLDF network. In 2007, though, they were upgraded to permanent status, and nowadays they are able to collect data seasonally. Indeed, their electrical supply is given by a set of solar panels and backup batteries that allow the system to operate only from the start of the austral summer season to the start of the winter austral season, because the sunlight at that point is no longer sufficient to recharge the batteries. And this usually occurs around the end of March. Then in the following year, the data need to be manually retrieved by some operators and are made available for download in the IGA website, usually in March of the year following the year of logging. Then finally, in the expedition 2014-2015, thanks to the collaboration with UNAVCO in the framework of Polonet and ANET projects, 3 of the 3 vertices of the aforementioned VNDF network were upgraded to permanent status. These 3 stations are VL01, VL12, and VL30. They are located respectively in Thomas Hill, Monte Cassino, and South Mount Bruce. These stations are equipped with satellite communication devices, so the collected data can be made available remotely for the download in near real time. Even though their power supply is given by the same system of the seasonal stations, which means again solar panels and backup batteries, in the case of the ExxonAlco stations, the system is able to work throughout the whole year, thanks to the fact that the pack of backup batteries is quite bigger with respect to the VL05 and VL18. To conclude the overview of the GNSS infrastructure managed by IGO, it's worth mentioning some of our ongoing collaborations and activities in support of other teams. The first one that I want to mention is the support that we've given to the MALOX project from INEA. MALOX project is its aim is to study the phenomenon of the snow transport over coastal areas that are characterized by heavy and strong winds. So for this reason, 2 different GNSS stations were monumented in Inexpressible Island and Mount Larsen. And these 2 locations are in a coastal area that is that represents the convergence zone for katabatic flux. And the data that collected from these stations are used basically to estimate the snow mass loss and for climatological and meteorological applications. Then, starting from the 29th expedition, we started, the ICOA observatory started a monitoring plan to control the deformation occurring on the boulder clay moraine. Indeed, during the 29th expedition, a gravel airstrip has been built on that moraine in order to help the Mariuzzi-Kelly station with logistic operations. So starting from that date, periodic surveys have been carried out using a network of 12 points that had been materialized with steel pillars. And the collected data is used to investigate the stability of the moraine over time. Finally, I would like to point out that last year we started a project for the monitoring of the deformation occurring in Mount Melbourne area together with the Volcanological Observatory. In this case, periodic surveys will be carried out with a local network composed by, as we can see from the bottom right-hand side image, 20 different points, of which 12 are used to materialize the framework, and the additional 8 are used as detail points. With that, the GNSS infrastructure managed by ICOA is completed. And now I would like to briefly present you a quick list of few results that can be obtained by the processing of GNSS long time series data. Again, my main intent in here is just to show you why this type of long-term geodetic observations are important, and what kind of insight it allows us to derive and infer. So if you're interested in the detailed methodologies and data processing procedures that can be applied in order to achieve these results, I encourage you to refer to the long list of related scientific papers and publications. So one of the straightforward applications for long GNSS time series is the opportunity to compute the absolute velocities, in our case in Antarctica, as Professor Scheinert has shown us while talking about the Giant Regain project. In Antarctica, these absolute velocities, as we can see from the left-hand side image, shows us the clockwise rigid rotation that the continent is undergoing to. And this behavior dominates entirely any other regional behavior. So how can we try to understand and to infer the regional behaviors? We can do that by inverting the GPS-derived motions, determining the Euler pole, and then going to subtract this rigid body movement of the entire plate, of the entire continent, to the absolute velocities. All of these processing allows us to determine the residual movements in regional scale, residual movements that basically highlight the behavior in regional scales, and are exactly these residual movements that allow us to understanding the regional displacement and deformation patterns. So for instance, this kind of reasoning is what has led to understand which of the faults present in Northern Victoria Land were actually active nowadays. And for instance, based on these results, in 2010, Dubini et al. Have presented and theorized a model of the Northern Victoria Land as composed by 5 main tectonic blocks and 2 smaller blocks. Once again, this didn't want to be an exhaustive presentation of the results obtained by the data collected over time, but I just wanted to show you what we can do, what we can achieve by the processing of the data acquired by such GNSS infrastructure. So with this, my presentation on the GNSS infrastructure managed by the IGOA comes to an end. But in my last few minutes, I would like to bring your attention to the fact that the 5th International Polar Year is approaching. And as we can see from the timeline posted in the IPY5 official website, the main phase of consultation and engagement with the polar stakeholders and research communities is coming to an end, as we are approaching the project phase that will start in 2025 and will continue till 2032, when the actual 5th International Polar Year will officially begin. But my main point is to highlight the fact that in the organizational structure of the IPY5, there's a specific group, which is the task group 4, which is explicitly focused on the involvement and coordination of early career scientists. This group, that is co-led by APEX, has begun its work in 2025, and its primary goal is to ensure the integration of the next generation of polar professionals and to be sure to involve them in the planning process of the 5th International Polar Year. So, as more information will be posted on the official website, I invite you to stay tuned and don't miss out this amazing opportunity. With that being said, I would like to thank you for your attention, and I am available for any comments or questions that you might have. Thank you again.
Thank you very much, Domitilla. It's very good that you mentioned the IPY.
Thank you.
Yes. Yes. Okay, I don't know if there are questions. Just raise your hand and speak up.
No, in the chat, there is no any question up to now.
No.
Then
But,
I will do 2 questions. Well, the first question is, well, the geodetic infrastructure of the Antarctica is very essential, but are there any works also to improve the topographic determination of the Antarctica by different other technique? Then you have the geodetic infrastructure, but to improve the digital elevation model or other topographic measurement, have you relationship or have you intention to develop this type of research?
Yeah.
I don't know if
Yeah.
by LIDAR or by other techniques. What is the
Yeah.
interaction between you and other groups that may do that?
Yeah, this is a good question. I mean, you could think about when I said that, of course, the determination of the surface of the Earth is one of the tasks of geodesy. So It could also be in our group, but in fact, it is nicely covered, I think. So we have a lot of different possibilities to determine the surface, the surface topography of Antarctica. So you can think the problem is that you, on the one hand side, you have the ice sheet, right? So there a lot of satellite missions are used, especially high resolution imagery. And this is mostly done, I would say now in a regular way, in let's say products which are updated also in a regular manner. So I just think about the reference elevation model of Antarctica, for instance, which is inferred from high resolution imagery using photogrammetric techniques, right? And of course, you can also combine the satellite data with, let's say, surface or near surface observations, as you said, like LIDAR or so. But due to the vast extension of Antarctica, you would never do it with, you know, these smaller patches of airborne surveys or so. This can, in my view, mostly be used to validate and to combine it with satellite data and maybe to improve some regional models, which has been done also in a number of cases.
Okay, thanks. And the second question, in order also to determine the gravimetry, you have continuous gravimetry measurement in order to see, I don't know, not only the tidal goal, but also the air tides or the long-term deviation in gravity fields in the observatory.
Yeah, this is different. I mean, the one thing is when you do gravimetric time series, then you would like to solve for Earth tides, which can be used, for instance, in other observations then, so to do reductions for relative and absolute gravimetry. You can also look for ocean tidal loading in order to validate or improve ocean tides. And of course, because the mass of the air above the gravimeter, so to say, right, is also influencing it directly, both due to the direct and indirect effects. But this is, let's say, a kind of side product. So to see the, let's say, the regression with the air pressure, right? So for gravity change, this is tricky. So because every mass change is influencing the gravimetric measurement, right? So due to the gravity or gravity anomaly being the first derivative of the potential, it's more localized, like for instance, the geoid or height anomaly. And I know, for instance, from our Scandinavian colleagues, so like I see Jaakko Mäkinen is there, he did a lot of absolute gravimetry observations in Dronning Maudland. And then also trying to combine the gravity change over time with the height change over time, you know, so in order to learn about the structure of the interior of the Earth and to the nature of the uplift and so on. But the problem there is that you have to very carefully determine the local ice mass changes. And this has, for instance, done around Aboa Station and also in other areas. So this is really, yeah, you are looking in the very last bit, you know, of
Yes.
and of course for the Antarctic mass balance, we are using satellite gravimetry, so from GRACE and GRACE follow on. There, of course, we don't have this high local or spatial resolution, but we have a much better temporal resolution in terms of 1 month or so, where we can infer the temporal gravity field in terms of spherical harmonics, for instance, or with any other base functions.
Okay, thank you for this nice presentation, Mirko and Domitila.
You're welcome.
Thank you.
I don't see any other question in the chat. I don't know if any people that is in the room, in the virtual room, may do another question to Mirko or to Domitila.
Or maybe to Domitila, I would like to ask if there is any starting discussion about IPY. For example, in thinking about in a multidisciplinary way, how you can connect with the other disciplines and just use the geodesy in general, for example, to think about traverse and try to fill the gaps where you don't have the data. You have very nice example of networks, for example, in Victoria Land, you extensively show how much you can get from such a nice network for a long time. But then you have most of East Antarctica, which is completely unknown. We don't know much about it. We don't know how it's moving, what's below. And so I wonder if you and the other young scientists start thinking about how you fill the gaps and have some sort of great broad project that you can work together, for example, for topography or for subglacial hydrology or for isostasy, across the grounding zone in the marine-based region. So something like that you can do it only in a large community with so many investment together.
Yeah, so thank you for your question. Thanks to the fact that my PhD is quite broad, like there are really a lot of different like PhD students from different backgrounds. We are actually trying to come up with some like doable projects that we would like to submit to our supervisor and then maybe to IPY. But yeah, for sure, there's like me and some other colleagues are starting to wonder if there's a chance to get more detailed information on the East Antarctic Craton, for instance, and how we could actually achieve that. So yeah, we are trying to understand what we could do.
Okay. I have a last comment or question. What the community may do in order to don't lost the PolNet network or UK network, because it is very difficult to set up a network, but it's necessary don't lose the monument or the points, even if there are many years that have not been measurement.
Yeah.
Then what is possible to do in this?
Yeah, it is my hope that and there are efforts to maintain the monuments at least, so because this is essential, so that whenever it would be possible to re-establish the instrumentation again and to have the same monument where to install the antenna, so this is essential. I think this process or these actions are still in process, so we are discussing a lot also in the instant group about this. And also I would like to add, so because Laura told about new projects on, so I still see that even after, let's say, decades of working in Antarctica, and I have experience now also for about 20-25 years, it's still logistics, which is very challenging and expensive. And with GPS, or let's say with all kind of autonomous instrumentation, so this is not only true for GPS, but also for seismology, for instance, for seismometers and so on. We get much more success if we have durable, reliable power systems, and if we have instrumentation which need much less power, right? So and also instrumentation which have satellite communication in order to transfer data. So as Domitilla showed for, I think, 3 stations or so you have there. Because if the power supply is really working and we have satellite communication, this then reduces the need to visit the sites. And this reduces also the logistical costs. So this is one of the key issues, I think. And I mean, progress has been made, but very slowly. So like, you know, piece by piece and so on. So, I mean, if there would be somebody from the young generation having that idea, which saves us to go to a station for 5 years or so, this would be great, right? And the other thing is that in Antarctica, I mean, and especially in terms of geodynamics, I mean, we have to fix our antenna to bedrock. And if you think about Antarctica, more than 99% is covered by ice. And this is the problem. This also limits our especially the GPS or the installation of GPS sites. I mean, there are also ideas to do precise measurements on the ice using an array, for instance, of radar instrumentations and so on. So, but this is also tricky. So that means whoever has some ingenious ideas on that, I think this is a wide field in a double sense to work on. Yeah.
Okay, thanks for the answer. Well, I don't found any other comments. Not in the chat. Okay, perhaps we may finish, no?
Yeah,
The
we
presentation.
thank Mirko and Domitilla a lot for their time, their effort. It was very nice. And I remind you that we have been recording the presentation, so you can watch the presentation later in the SCAR Geoscience portal. And perhaps if there are more questions, I think they can redirect to you, Mirko and Domitilla. And perhaps you can say how people could be involved into this expert group in the future. What do you suggest?
Yeah, I mean, you can just have a look at the SCAR website and you will find our group, so Expert Group Giant, and I think there also the contact details should be given. So just drop me an email. We also maintain a mailing list, so whoever is interested can also subscribe to that mailing list.
Okay.
Okay. Well, thanks, Domitilla. Thanks, Mirko.
Thank you.
Nice to see you, Alexandro. Now.
That's true.
Okay.
And
also
thanks to Mirko and Domitilla. Really thanks.
Yeah.
Okay.
You're welcome. Yeah. Thank you for your attention and joining this webinar at this late time. So now I can open the bottle of wine.
Yes, now you can.
Okay.
Yeah, thank you again
Okay.
for the opportunity. It was a real pleasure.
Okay.
Yeah.
Then see you in the next webinar. Okay.
Yeah.
Ciao,
Thank you.
Laura.
Bye.
Bye.